Okay, let's begin. So, in the last lecture, we have we have been looking at propositional logic. Propositional language is simply a set, usually countable, often finite. What letter do we use to denote the elements of the language? PQR, yes. So, they are called propositional variables. And from those propositional variables as letters in the alphabet, we construct sentences or formulas. What are those formulas? What symbols do we use for them? S and T and U. Okay. Then SL is the set of all propositional formulas for a language L. There are some formulas which are well formed. We only define well formed formulas. And the rest of the strings or words formed out of those symbols are not formulas at all. Then we also saw that the concept of a valuation. Correct? A valuation is, after proving a result, valuation is simply a function from L, the language, to the two element set, truth or false. Right? Okay. Now, today we are going to look at something more syntactic. So, syntactic as in how do we write a formula? Not every formula can be written in multiple different ways. We only use actually negation and conjunction. Negation is a unary connective and conjunction is a binary connective. Then using De Morgan's law, we also introduce disjunction. Then we have also talked about implication and by implication. Now, if our language, if our meta language has got negation, conjunction, disjunction, then we can talk about some specific types of formulas. And those formulas are said to be in the normal form. So, that's our first topic for today. So, what are formulas in normal form? So, we will need some definitions. So, start with let L be a language, be a propositional language. Okay. So, so for P in L, say that P and negation P are literals. So, this is literal is a concept which is coming from languages itself. So, in linguistics we say, like, if I am uttering the word logic, then how many times am I stressing it? Logic. So, only two syllables are there, sort of. So, similarly literals or syllables, that is a name for these simple things. So, P and negation P, these are literals. A formula S in SL is said to be in the disjunctive normal form I am underlying disjunctive normal form in bracket DNF. So, that is how we normally pronounce it. If it is of the form, so disjunction of conjunction of literals. Okay, of course, these are finite sets. We are taking disjunction of finitely many conjunctions of literals. Okay, so let me give you an example. So for example, P disjunction Q is in DNF. Yes, why? Tell me what exactly is happening here. P disjunction Q, why is it in DNF? It is the disjunction of P and Q, and P is singleton conjunction, Q is singleton conjunction. Similarly, I can also say that P disjunction negation P and Q, that is also in DNF. Can you see why? Yeah, the first part is P. P is a conjunction, singleton conjunction of literals, and negation P conjunction Q. Yeah, negation P is a literal, Q is a literal, and then it is a conjunction of literals. Is that okay? Any questions?
Sir, both are finite.
Both of them are finite. Yeah? I mean, P is a singleton conjunction. Our formula cannot be of infinite length. Yes, so everything has to be finite. Then, what about this? P conjunction Q or negation P conjunction Q. This is also in the DNF. And one more thing, can you observe? All these three formulas are logically equivalent. Okay. So all of these formulas are logically equivalent. Like maybe I can tell you the more specific form of this. So generally we write it like this. So disjunction I running from 1 to n, n could be 0, yes, of conjunction j running from 1 to mi, yeah, because this is inside thing, and then pij to the power sigma ij, okay, where pij's are in L and sigma ij's are in plus or minus 1. Okay, so let us see how to make sense of this. If I write p to the power minus 1, I am actually talking about negation p. Yeah, so so all of you understand this? Yeah, though that there is mi. So mi, that index depends on I. Okay, well, there is something that you need to know. Yeah, so for any set, for any formula, any finite set of formulas, conjunction of S and disjunction of S is a formula. Yes, I am simply taking conjunction of all of them. But when I write these notations, there is also something you should be warned about. So what is and this conjunction of the empty set of formulas, because I wrote if S is a finite set of formulas, then their conjunction and disjunction should make sense. So what about the empty set of formulas? What is empty conjunction? Huh? Empty conjunction is empty. See this, what did I write? Please read the whole sentence. Conjunction and disjunction is a formula. So empty, can it be a formula?
P conjunction negation P.
P conjunction negation P. Now let's think about it, okay? What is conjunction? Conjunction is, in the Boolean algebra sense, it is meet. So meets are always smaller. Yeah, you try to go down. So if I have singleton conjunction, then I'm just there. Yeah, it is P. Then I take P conjunction Q, then I will go down. P conjunction Q conjunction R, I will go even further down. Then what should be the empty conjunction? Yeah, I mean, if this is 1, 2, 3, then where should be 0? Top. So it should be above everything. So that's how you should always think about it. So empty conjunction is a tautology. And dually, the empty disjunction is a contradiction. All of you understand this idea? If you put more constraints, conjunction is like you want this and this and this and this. If you don't want anything, then you might as well be the top element. There are no restrictions. Okay, so this is a tautology. And this is a contradiction. Meet goes down, correct, but if there are more elements, then the meet goes down further. So if there is no constraint, S you should think of as the set of constraints that you want to achieve. If there are no constraints, then you are at the top. You put more and more constraints, then your element is lower in the Boolean algebra. That's okay? Okay, so one more example perhaps I can add to this list. So this one, P conjunction Q, that itself is in disjunctive normal form. Can you see that? Why? Can you tell me what is I, what is J? What is N? N is 1. And what is M1? 2. Are you getting? Yeah. So now what to do with this disjunctive normal form? Yeah. What is the purpose of it anyway? If I want to evaluate the truth value of a disjunctive normal form, then what will happen? When is P disjunction Q true? When one of the P's and Q's is true. When is this arbitrary disjunction true? When one of the conjunction of literals is true. When is a conjunction of literals true? When all the literals are true. And from literal you can literally, yes, from literals you can literally check its truth value. Yeah, P conjunction negation Q conjunction R. If I say that, when is it true? P and R should be true and Q should be false. Right? So that's how. So finding out truth values of formulas in DNF is really easy. And you can teach this to a computer. Yeah, I mean you can of course teach a lot of things, but these are logic gates. Yeah, just conjunction and disjunction. Okay, so I'm just going to write down a theorem. Yeah, the proof is very easy. If S belongs to SL, then there is T in SL such that T is in the DNF and S is logically equivalent to T. So I am not claiming that every formula is in DNF. I'm claiming that every formula is logically equivalent to a formula which is in DNF. So here, warning, T may not be unique. Most likely it is not. Yeah, I mean we saw these examples. First 3 elements in this list, they are logically equivalent. They are all in the DNF. Correct? So T need not be unique. There could be multiple formulas in the DNF which are logically equivalent to each other. Okay, let us do one exercise. Please try to write down this. P implies negation Q. Yeah, write down this formula up to logical equivalence in the DNF. And tell me the answer. Yes? Tell me. P conjunction Q. Negation P. Disjunction negation Q. Okay. That is one easy formula which is in the DNF. Yeah. There was no negation here. Then you can also perhaps write down more. When I write this, then what is N? N is 2. What is M1? M2? Good. Okay. Now tell me the proof of this theorem. If I am given any formula, well, one thing that you know for sure is that every formula has finite length. So how many variables can it use? Finitely many variables. Good. So now only choose those finitely many variables from your language which appear in this formula. Yeah. Then construct the Lindenbaum-Tarski algebra. Right. Then this formula S, yeah, that S will have its logical equivalence class in that Boolean algebra. So that logical equivalence class in the proof of stone representation theorem, this is a finite Boolean algebra. So in the proof of stone representation theorem, we saw that every element is the disjunction of all the atoms below it. What do atoms look like? Atoms are always conjunctions of literals. Right? So therefore every element is a disjunction of conjunction of literals up to logical equivalence. That's precisely the proof. Let us do it properly. Now I'm just saying the same thing. Yeah, P implies negation Q. Yeah, what is the logical equivalence class? What atoms lie below it? This is negation P, disjunction negation Q. So which atoms will lie below it? Negation P, that's not an atom. So how many variables are there in this formula? 2 variables. So how many atoms are there? Well, you have also written 6 in the exam, but okay, so 4 atoms. So out of those 4 atoms, there are 3 atoms which lie below this. Okay, so the first atom is negation P, conjunction Q. This is the first atom. Then disjunction P conjunction negation Q, and disjunction negation P conjunction negation Q. So these are the three atoms which lie below this formula, and therefore this is my disjunctive normal form, and that is like the standard disjunctive normal form. You can always obtain it via an algorithm by following a procedure. Okay, so what did we do? We took the logical equivalence class of this formula in the Lindenbaum-Tarski algebra. We looked at what sort of atoms lie below it, and then we took their disjunction. The atoms are always conjunctions of literals, and therefore we are done. Now what will happen if I start with a tautology? All atoms will take disjunction of all the atoms. And what if I start with a contradiction? No atoms. So in that case it is disjunction of not phi. Phi is not this symbol. This is empty set, Norwegian symbol. So disjunction of empty set. Okay, so that's the proof of the theorem. I am not writing it. Homework. Right. Dually, we also have conjunctive normal form. I am just going to write it here. Yeah, CNF. It's very simple. It is conjunction of disjunction of literals. So instead of atoms, here we use coatoms, and everything else is exactly the same. Coatoms are the elements which are just below the top element, if they exist. Well, they will always exist. For a given formula, there are only finitely many variables which appear in that formula. So we are anyway constructing a finite Boolean algebra. Okay, perhaps tell me how to write a particular formula. I am going to give you this. P if and only if Q. Yeah? Tell me how to write it in conjunctive normal form. So you had to look at all the coatoms which lie above it. The coatoms can always be written as disjunctions of literals. So can you tell me what are the coatoms in this two element language Boolean algebra? P disjunction Q, negation P disjunction Q, P disjunction negation Q, and negation P disjunction negation Q. So 4 of them. Which coatoms will lie above this? Negation P, disjunction Q, yes, right. So negation P, disjunction Q, this is P implies Q, yeah, and then we are taking its conjunction with, yeah, P disjunction negation Q, okay. So for a tautology, how do we express it in a CNF? It is conjunction of empty set, and the contradiction is disjunction of what? Conjunction of all coatoms. Okay. Any questions? This is simple. Good. Let us do one more syntactic thing. I mean, this is semantic, not syntactic. So our next topic is going to be truth functions. So truth function, what are they? So any function, an n-array truth function, is a function f from the nth power of this two element set to itself. In computer science, this is also called a Boolean function. It is a function from 2 to the power n to 2. How many n-ary truth functions can there be?
2 to the 2.
Number of n-ary truth functions. How do you compute such number? It is the cardinality of this set of functions from A to B, which is cardinality of codomain to the cardinality of domain. So cardinality of codomain is 2. So 2 to the power n. Okay. And do you know anything else that has this cardinality? Finite Boolean algebra? Which one? Right. Lindenbaum-Tarski algebra. So, will it come as a surprise to you if I said that there is a bijective correspondence between truth functions and, so yeah, I mean, let me write the theorem. There is a 1-1 correspondence between the set of n-ary truth functions and the LT algebra BL, where size of L is equal to n. Okay, so what is a truth function doing really? It tells you that if there are, so choosing an element from top bot to the power n, what does that mean? It's a finite sequence, right? It's a finite sequence of truth values, and it's an ordered sequence. Yeah, at the first position I am choosing T, at the second position I am choosing bot, top, bot. Yeah, so it's a sequence. So basically, whenever I have, let's say, 3 variables, then what I am doing is, if I have 3 variables, then P, Q, R, I am simply assigning each one of them a truth value. So I am saying, okay, let me say that these two are true and this is false. And then the value f of this. Yeah, so basically we are talking about a row of the truth table, and value of this function would be whatever happens next. So, okay, maybe I'll do a simpler example. I'll get rid of this and do an example of this form. So maybe a 2-element truth function. Yeah. So if I am given T, I need to give a truth function. Yeah, so this is the f. So now I am going to say, so yeah, this is, let's say, a and b, and then I am writing down f of ab, and my function is given like this. Okay, this is my graph of the original function. Do you understand that this table describes a truth function? What is n here?
2.
Okay, good. So n is 2. So for all different values of ordered pairs A comma B, I am describing what is f of AB. Now, in order to make this theorem true, you still have to find out what thing it is, what function it is. What does this say? That it is in one-to-one correspondence with the elements of the LT algebra. So, which means you have to find one formula whose truth table looks like that. Can you find that formula? A is not a formula. Yeah, you have to first choose a language. Yeah, so you are telling me that so f is in bijective correspondence with the formula P, just P. Yeah, I mean there is nothing else, right? And if you do not know how to find it, yeah, I mean perhaps I can make a little change over here. I can say this is T. Okay, tell me if this for this formula now.
A conjunction, P disjunction, negation, conjunction, negation.
So this is my G. Okay, so G is in bijection. G corresponds to
A conjunction, B disjunction, negation, conjunction, negation.
Okay, what's the process that's going on in your head? Huh? Yes, I mean, see, you can always find the answer, but explain the process to me. Two true values, yes. So, you are actually constructing a DNF. Can you read that DNF from this table? Yes? So, you look at all the things which make it true. And then you are looking at the disjunction of both of them. So, let me write, so these two rows, right? Okay, from the first row I can get P conjunction negation Q. P conjunction negation Q will make the second row true. And for the third row, negation P conjunction Q, and then both of only these two are true, so I just take their disjunction. So the disjunction will be true only if one of them is true. So are you getting the method? So basically, however many variables are given to you, if you are given a truth function, then you simply look at what all things are the last column of the values, yeah, of f, and then you look at which of them are true and take corresponding rows and write down the corresponding atoms which make them true and take disjunction. So you can always find a formula in the DNF which corresponds to a truth function. And conversely, given any formula up to logical equivalence, the truth table gives you a truth function, the truth table of a formula. Yes? All of you understand truth tables. You simply have all the variables P1, P2, Pn, and then finally the formula, the truth, the column for the truth values of the formula. That is a truth function. So there is a one-to-one correspondence between truth functions and the logical equivalence classes of formulas. Do you want to do one more example? Yeah? So let me tell you something in black color now. Yeah, this is function h. So what does h correspond to? P conjunction? P conjunction negation P. Okay. Fine. So you understand truth functions now? Okay. Now truth functions are really important. So for example, I write down this particular truth function. A, B, then f of AB. This particular truth function, let us see if you can identify what I am writing. Do you know the name of this? NAND. Very good. NAND means N and, negation of and. Yeah. So actually, if you have used NAND before, then NAND is itself sufficient to describe negation.
The third column should also be false.
No. Third column should be false.
Row.
No, third row should not be false. So NAND is a binary operator. NAND is a binary connective. Yeah. Okay. And if I take just, so does there exist a formula that only uses NAND and describes not describes, and is logically equivalent to negation P? Yes, tell me how. Are you understanding the question? The formula cannot use negation, it cannot use conjunction, disjunction, implication, by implication, anything. It should only use NAND. P NAND P. Okay, so let us try to write down the table for P and P NAND P. Okay, if this is true, then true will give me false, and if this is false, then you have to look at this particular green table. Yeah, so false and false should give me true. So P NAND P is sufficient to describe negation P. Now tell me if only NAND is sufficient to describe P conjunction Q. So P conjunction Q. Yeah, you want the truth table of P conjunction Q, but you can only use NAND.
A NAND B, NAND with A NAND.
Yes, okay, so you are experienced with this. So P conjunction Q is logically equivalent to P NAND Q NAND P NAND Q. Yeah, please verify this, that this does happen. Okay, so now what happened? NAND was a single binary connective, and from that single binary connective I could write negation and I could write conjunction, and all our formulas are constructed only using negation and conjunction. So therefore every formula is logically equivalent to a formula that only uses NAND. We express this fact by saying that singleton NAND is an adequate set of connectives. Okay, so let me write this down. Okay. A set C of connectives, I will leave some space here, is said to be adequate. Adequate means sufficient, simple English word, if given any formula there is a formula T that only uses connectives only from C such that the truth tables of S and T are the same. So, for example, is adequate. Yeah, we just showed that. Then, similarly, this is what we normally use, negation and conjunction. Can I replace conjunction by disjunction? Yes? So, I will just write more. Then, negation and implication. Is this adequate?
Yes, sir.
Yes? There is something to be checked. Then, so is yes? What about this? Why? Why is this not an adequate set of connectors? Sorry, loudly.
Because you cannot consider all the atoms of the algebra.
We cannot write atoms of the LT algebra.
Yeah, like
Even if sometimes you are able to write all the atoms, and then is that sufficient? Formula would be opposite.
the language has more than one element. You can't.
Language has more than one element.
Then you can't combine any two elements in any way using.
Combine in what sense? These are vague words. Make it precise.
Can't describe their conjunction.
You cannot describe conjunction. Very good. And how do you prove that? You cannot describe conjunction using negation. How do you describe that? Negation is unary operator. Okay. Now we are using these words interchangeably, right? Unary operator, unary connective. So there is a blank space at the top. What is the meaning of connectives? What is a connective? Does it have to be binary connective? No. It can be unary, it can be ternary, it can be four-ary, anything you like. So it can be n array. So what is a connective? Loudly. N array function, arbitrary function. You are close but not there yet. N array truth function. So a connective is nothing but a truth function. Okay. So that's what I mean. Let me fill that gap. So this is a truth function. Of any array T bigger equal 1. Okay. So this is not, yeah, apparently you are saying this is not adequate. Because, so look at what is the meaning, I mean what is the definition. Definition says that it is adequate if every truth table can be drawn using only connectives from this set. However, we are not putting any size restrictions on the arity of the truth table or truth function. Truth table is same as a truth function. Yeah, so we are starting with a set C, fixed set C of truth tables or truth functions, and then given any even 100 array function, truth function, I should be able to describe the last column of that truth function using connectives from C. That's our goal. So it's not just restricted to a particular array T. It can be 1000, 1 million, anything. And that is what we normally do. When we say that negation and conjunction are adequate, well, every formula is logically equivalent to a formula which can be written using negation and conjunction. So when we say that something like this is not adequate, then we are actually trying to find out a truth table of some array T, some small enough array T, which cannot be described by using negation. Are you getting what we are saying? So this is not adequate. Similarly, this is not adequate. Yeah, just conjunction alone is also not adequate. And here my argument is going to be whenever, yeah, I am just going to write the argument for the second one. Whenever V is a valuation on PQ such that V of P is true, then for every formula L formula, I mean this is my L right now, constructed using only conjunction, yeah, then for every L formula S constructed using only conjunction and that contains P, what should I say? The value, so what will be the value of P? So sorry, I did not want to say P and Q, yeah, please excuse that. I just want to say 1. So Then for every formula S constructed using only satisfies V of S equal to true. So use induction here. Use induction to prove this. Because what are the formulas that you can construct? You can construct P conjunction P conjunction P conjunction P. So everything is boring and you will only get value true. You can never actually obtain the value false. So therefore the truth table for negation P, that is a truth function. It is a unary truth function. That can never be obtained by using only conjunction. And therefore this is not adequate. Now similarly try to prove that singleton negation is not adequate. Yeah, but here you need to use induction, right? So keep your language small enough and then try to prove that negation is not adequate.